Now we're thinking about waves, but to keep it simple, we'll start by just thinking about one pulse traveling down through some medium. And the simplest medium that we usually think of is a wave traveling on a string. Uh, Much of what we say for a wave traveling on a string will be true for all kinds of waves. So again, it's a nice simple model for many different kinds of waves. Now, let's say I grab onto the left end of the string. Uh, Here's the way the string would look if it were just undisturbed, if I were not shaking it at this end. And let's say that I just give the string one shake. Pull the left end up and then pull it down. That'll produce a pattern like this. Right? This part of the pattern happened when I pulled the string up, and then this part of the pattern happened when I pulled the string down. This pulse shape here doesn't stay there. It moves down the string because this end of the pulse pulls on pieces of the string immediately in front of it. For example, this pulse is pulling on this little piece of the string here. Imagine this little piece of string is just one bit of mass and there are two forces acting on it. The string tension from this part of the string to the left, and then the string tension from this part of the string to the right. And like always, string tensions always point right along the direction of the string, and the strength of the string tension depends on how much the string is stretched. The string is like a spring. It's an elastic object, not as elastic as a spring, but still it's elastic, so that when the string gets stretched, and obviously it's getting stretched here, its original length was just this far, but now this piece of string has been stretched so that it's a bit longer. That when a string gets stretched, it'll try to snap back to its original shorter length, and as it tries to snap back to its shorter length, it'll pull on other pieces of the string. So this little point here has two forces acting on it. The tension force from the left-hand part of the string is pulling this way, and it's strong because this part of the string is stretched a lot. And then the tension force from the right-hand part of the string pulls this way, and it's much less strong, it's much weaker, because this piece of string is stretched much less. Just like a spring, this works for any elastic object, whether it's literally a spring or just another elastic object that behaves like the spring. Anytime you stretch it, there's a restoring force trying to get it to come back to its original shape, and the more you stretch it, the stronger the restoring force. So this little piece of string is stretched less, so the restoring force that it applies to this little bit of mass is smaller. But two different forces, so there's a net force on the string. And what's that net force like? You've got the tension from the left-hand string pulling this way, and you add to it this tension here, and so the net force will be a force just straight up. The leftward pull of the weaker tension was just enough to cancel out the rightward pull of the stronger tension, so that the net force is simply vertical. And we could look at another example of that right here. Just imagine this point here. This point is being pulled down by the bits of string to the right of it and to the left of it, somewhat like this. So to the right, there's a tension force from the string to the right, and then on the left, pointing at a steeper angle, there's a force a stronger force, this part of the string being stretched more than this part of the string, a stronger force. So those two forces add again to give you a net force. And what's the net force like when you add those two forces together? You've got the strong force, and then you add to it that other force up and to the right, so that again the net force points down. This little bit of mass is now being pulled down by the net force on it, and eventually this little bit of mass will return to its normal undisturbed location, or in other words, its equilibrium location. But in any case, remember, this piece of string was being pulled up. It's going to keep on being pulled up until it's at its maximum distance away from equilibrium, and at that point it's going to start coming down, because now there's a restoring force acting on this little bit of string, trying to pull it back to its original equilibrium position. And for example, what that means is that now the peak of this pulse has moved from here to here, because this little bit of mass has been pulled up for a while, so that now it's at the peak displacement. So now the peak displacement is right here, consisting of this little bit of mass. And what's the net force on this little bit of mass? Well, there's tension pulling this way from the string to the left, and there's tension this way pulling from the string to the right. Right around this point, everything looks pretty symmetric. So the tension pull from the right-hand string is really symmetric to the tension pull from the left-hand string. They're both the same strength. And they're both at the same angle with respect to horizontal. So that when you add those two forces together, the pull from the left plus the pull from the right, again, you end up with just a vertical force. Right? The leftward component of this force is canceled out by the rightward component of this force, and all you're left with is a vertical force, a force pointing down, a force pulling this little bit of mass back towards its equilibrium position, exactly what a restoring force does. And so now this little bit of string is now being pulled up, just like this one was a little bit earlier, so that eventually this little bit of string will be pulled up until it gets to the maximum displacement, and then at that moment the peak of the pulse will be right there, and the pulse will look like that. In other words, after I give the left-hand end of the string a shake, the pulse just moves from left to right. And if I, instead of giving it just one shake, I continued shaking it for a while, I'd have not just one pulse moving to the right, I'd have an actual wave moving to the right. But to keep things simple right now, we'll be looking most of the time at the movement of just pulses with simple shapes, because a wave would actually behave the same way. In the reading, you saw that there are two ways to visualize the motion of a wave through some medium: snapshot graphs and history graphs. So let's just look at a snapshot graph for a simple-looking pulse moving on a string. So remember what a snapshot is. It shows you what kind of disturbance or displacements different bits of mass at different locations have at one point in time. Just like an actual photographic snapshot shows you what a whole bunch of different things look like at one time. And so to keep it simple, we'll call this time 0. And since the snapshot shows you what different bits of mass at different locations are doing, this will be a graph of actual displacement away from equilibrium as a function of location. And we'll mark off the location in centimeters here. So 1 to 5 centimeters. And we'll say that our pulse looks like this. And we'll say that the velocity of the pulse points to the right. That is, that pulse shape is moving this way along the string. And we'll say that the speed of that pulse is 100 meters per second. A little trick that we do to make the graphing easier. We ask ourselves, how much time, if this is the speed, how much time does it take for the pulse to move 1 centimeter? Well, 100 centimeters per second. If it moves 100 centimeters in 1 second, then it would move 1 centimeter in 1/100th of a second. So when we get to the so-called history graphs, we'll be marking off the horizontal axis, as we'll see in a minute. We'll be marking it off in units of hundredths of a second. But first, let's imagine what other snapshots would look like. Other snapshots of this same string would look like at later times. The pulse is moving to the right, so at later times we would see this same shape shifted over to the right. And as time went by, we'd see this same shape farther and farther to the right. Well, how much farther? Let's since the pulse travels 1 centimeter in 100th of a second, it's easiest to think about the snapshot that happens 1/100th of a second after this time. Displacement versus location in centimeters. So let's think about this. This pulse moves with a speed of 1 centimeter in 1/100th of a second. What that really means is that if you pick any piece of this pulse, that piece moves 1 centimeter to the right in each 100th of a second. So here, the front edge there, or the leading edge, you might call it, of the pulse in 1/100th of a second moves from here to here, from the 4 centimeter mark to the 5 centimeter mark. And this this piece of the pulse here, the bottom of the valley, also moves 1 centimeter from 3 to 4 in that amount of time. So now the front of the pulse has moved from 4 to 5. The valley of the pulse has moved from 3 to 4. And this point here right in the middle has moved from 2 to 3. And the peak has moved from 1 to 2. And the back end of the pulse has moved from 0 to 1. And then just do this again just to reinforce the idea. Now, one more snapshot graph at 0.02 seconds. In other words, 1/100th of a second after this. So in that 1/100th of a second between this time and this time, that pulse would have moved another 1 centimeter to the right. So a snapshot would look like this. The front of the pulse was at 5, and then 1/100th of a second later, it's moved 1 centimeter to the right, so 1/100th of a second after this, at 2/100ths of a second, in other words, the front of the pulse will now be at 6. And the bottom of the valley will also have moved 1 centimeter in 1/100th of a second. So by the time you get to this time and this snapshot, the valley has moved 1 centimeter from 4 to 5. And the midpoint has moved 1 centimeter to the right in 1/100th of a second. It's moved from 3 to 4. And then the other half of the pulse looks like that. So that's what snapshot graphs are like. That's how we think about snapshot graphs. The other kind of graph is a so-called history graph. Instead of looking at the displacements of a whole bunch of different locations all at one time, right? All the displacements between the 0 and the 4 centimeter mark at time 0, or all the displacements between the 1 and the 5 centimeter mark at time 0.01 seconds. Instead of doing that, we kind of flip it around and we look at all the displacements for just one location as time goes by, all the displacements that one little bit of mass goes through at different times. So let's, just as an example, let's take the x = 5 point as the point that we'll be focusing on. We'll draw a history graph for the motion and the displacements of this point here. So, by drawing a bunch of snapshot graphs for different times, you can easily see how the little bit of string, the little bit of mass at the 5 centimeter mark has been moving. And we can represent that motion on a graph of displacement versus time. So here's a history graph for the x = 5 point. Displacement versus time. Well, right at time 0, the front of the pulse had not yet arrived at 5. In other words, at time 0, the 5 centimeter mark was still in the in the bit of string that had not been displaced away from equilibrium. So time 0, the x equal 5 centimeter point hasn't been displaced yet. But 1/100th of a second later, the front of the pulse arrives. So since our snapshot graphs are taken at 1/100th of a second intervals, then the naturally easy way to number along the time axis is in units of hundredths of a second. So at 1/100th of a second, that's when things start to happen. That's when the front of the pulse arrives at x equal 5, as we see here. But previous to that, since the pulse hadn't arrived, nothing has happened to the x equal 5 centimeter point, so it just stays at its equilibrium position. 0 displacement away from equilibrium. Well, in the next 100th of a second, between 0.01 seconds and 0.02 seconds, look what's happened by the end of the second, the x equal 5 point has been pulled down to its maximum displacement on the negative side. So at 0.02 seconds, the displacement of the x equal 5 point is like that. And so what must have happened at times between here and here was that this piece of the pulse was passing through the x equal times between here and here, this piece of the pulse was passing through the x equal 5 point. And as it did, it gradually pulled the x equal 5 point down to its greatest displacement on the negative side. So just imagine this kind of shape passing through when this much of the shape has passed through, then at a later time, later than 0.01 but still before 0.02, the front of the pulse looks like this. So at that moment, the 5 centimeter point has been pulled down that far, and then a little bit later, the front edge of the pulse looks like that. So at that moment, the 5 centimeter point has been pulled down that far. So in that 100th of a second, gradually being pulled down. This piece of the pulse is 1 centimeter wide. So since the pulse travels at 1 centimeter in each 100th of a second, it takes 1/100th of a second for this piece of the 1 centimeter piece of the pulse to completely pass through the x equal 5 point. And then in the next 100th of a second, this 1 centimeter piece will pass through. So that by the time you get to 0.03 seconds, this piece of the pulse is now at x equal 5. The pulse shape looks like this. And the middle piece of the pulse is now at x equal 5. And then get to 4/100ths of a second. And now this 1 centimeter, in the time between 3 and 4/100ths of a second, this 1 centimeter piece of the pulse is passing through, so that by the end of that 100th of a second, the x equal 5 point has moved from equilibrium up to its maximum displacement away from equilibrium, like that. And then in the last hundredth of a second, this piece of the pulse passes by, so that by the end of that hundredth of a second, the tail end of the pulse is at 5, which means that's the very last moment when the x equal 5 point will experience any displacements at all. Like that. So that's the history graph. According to the history graph, the pulse arrives, the front edge of the pulse arrives at the x equal 5 point. At 1/100th of a second, and then the back end of the pulse passes by at 5/100ths of a second. Or to put it another way, at time 0, the back end of the pulse was 5 centimeters away from the x equal 5 point. And since the speed of the pulse is 1 centimeter in each hundredth of a second, if the back end is 5 centimeters away, it will take 5/100ths of a second for the back end to arrive at x equal 5. So the back end arrives at x equal 5 5/100ths of a second after this. In other words, at this time. So let's look at just one more like this. Well, a couple more actually. Instead of a history graph for the x equal 5 point, let's look at a history graph for the x equal -1 point. What I'm assuming here is that there's more string to the left of x equals 0. I just put the x equals 0 mark somewhere in the middle of the string, not at the left end of the string, but somewhere in the middle. So at times before this, the pulse was farther to the left, because as time goes by, the pulse moves from left to right. So when you look at earlier and earlier times, the pulse will be farther over to the left. For example, at negative 1/100th of a second, the displacement versus position snapshot graph would look like this. That is, since the pulse travels 1 centimeter in 1/100th of a second, then 1/100th of a second earlier than this, every piece of the pulse would be 1 centimeter in the backwards direction. You go 1/100th of a second backwards in time, then you see the pulse 1 centimeter farther in the backwards direction. So at minus 0.01 seconds, the front edge of the pulse was at x equal 3. And then in the 100th of a second, between minus 0.01 and 0 seconds, the front edge of the pulse traveled 1 centimeter, so it went from 3 to 4. It's at 4 1/100th of a second after this time. And then if you go back to earlier and earlier and earlier times, you'll see the pulse passing through the x equal -1 point. For example, just 1/100th of a second before this, in other words, at the time of minus 0.02 seconds, the displacement versus location graph would look something like this. 1/100th of a second earlier than this, every piece of the pulse would have been 1 centimeter in the backwards direction. So it would look like that. One thing that you can see is that now if we were to draw a history graph for the negative 1 centimeter point, one thing we see by comparing all these snapshots is that the back end of the pulse leaves the minus 1 centimeter point at this time. The last piece of the pulse passes by the minus 1 centimeter point at this time, so the rest of the pulse must have been passing through that point at even earlier times. But we can see, for example, at 1/100th of a second before this, the peak near the back end of the pulse was just passing through the minus 1 centimeter point. So let's draw the history graph for the minus 1 centimeter point. X equals minus 1 centimeter, and so displacement versus time, right? The displacement of the little bit of string at the x equal minus 1 centimeter point, how that displacement changes as time goes by. And again, since the pulse moves in nice simple 1 centimeter steps in each 100th of a second, we'll make the units on the time axis hundredths of a second. Or like that. Okay, one thing we saw was that the disturbance and the displacements of the minus 1 point ended right here at this time, negative 1/100th of a second. At all later times, this pulse was past the minus 1 point. This pulse is moving to the right, so that at all times after this time, the pulse is getting farther and farther away from the minus 1 centimeter point, so nothing is happening any longer to the minus 1 centimeter point. It doesn't have any displacements from, so at all these times, zero displacement away from equilibrium. Okay, well, this is where the pulse finished moving through the x equal minus 1 point. 1/100th of a second before that, the peak was passing through. And then in each 100th of a second, a 1 centimeter segment of the pulse is passing through the x equal minus 1 point. So this piece of the pulse is right in front of this piece. Remember, the pulse is moving this way, left to right, so this piece is in front of this piece. So this piece being in front, it must pass through the x equal minus 1 point before, at earlier times, than this one does. And since this pulse is, again, this piece of the pulse is again 1 centimeter wide, it takes 1/100th of a second for this piece to pass through. So that piece was passing through in this 1/100th of a second here. And then thinking the same thoughts for the rest of the pulse, the history graph would look like that. Notice that it's exactly the same shape for the other history graph that we drew, and that makes sense because the same pulse passes through both of those points. So it's going to do the same things in the same order to both of those points. It'll just do it at different times, that's all. Another way of looking at all this is that at minus 1/10th of a second, the pulse was finished moving through the x equal minus 1 point. That is, the back end of the pulse arrived at the x equal minus 1 point. But the front and back ends of the pulse are 4 centimeters apart. The pulse is 4 centimeters wide, and the pulse travels 1 centimeter in each second, so it takes 1 centimeter in each 100th of a second. So it takes 4/100ths of a second for the whole pulse to pass through. Meaning, if the pulse was finished passing through at this time, it must have started passing through the x equal minus 1 point 4/100ths of a second earlier. In other words, at this time. Okay, one more example. This time, instead of looking at a bunch of snapshot graphs and using those to figure out what a history graph looks like, we'll compare one snapshot with one history graph, and we'll be able to deduce some information from that. So here's a snapshot graph, and we'll say this was taken at a time that we will call x equals 0. So being a snapshot graph, it's a graph of displacement versus location. The snapshot tells you what's happening at different locations at one point in time, and at that moment in time, the displacements caused by the wave look like this. We'll say it's marked off in centimeters again, so that in this case, the wavelength of this pulse is 4 centimeters. Now, a history graph of this point, right, the history of the x equal 2 point, so how does this point bounce up and down while the pulse is passing through as a function of time, displacement versus time? Let's say that that displacement pulse looks like this. And again, we're marking off the time in hundredths of a second. And the history looks like this. Well, one thing, even before we draw the history graph, there's one point that we know for the history graph just by looking at this. We know that at time t equals 0, the x equal 2 point was right at equilibrium. And then how does it move at later times? It moves like this. That is, this history graph shows us that right at time 0, must have been the middle of the pulse that was passing through. At the earlier times, the valley passed through, and at later times, after time 0, the hump, the peak, will pass through. So that 1/100th of a second after this, then the high peak will be passing through. Which means 1/100th of a second after this snapshot, the snapshot would look like the snapshot for 1/100th of a second would look like this. So this happened at earlier times. In other words, at minus 0.02 seconds, the front edge of the pulse first hit the x equal 2 point and started displacing the x equal 2 point. The first thing the pulse did was pull the x equal 2 point to negative displacements, which means this is the front of the pulse. This part of the pulse will be pulling any point down to negative displacements. This part will be pulling any piece to positive displacements, which means this is the front, this is the back. In other words, when you compare this snapshot with this history, you can figure out that in this case, the velocity of that pulse was pointing to the left. The pulse was moving to the left. And you can see that by comparing the snapshot at 0 seconds to the snapshot 1/100th of a second later. In 1/100th of a second, the back end of the pulse moved to the left from here to here, right, at 1/100th of a second. The back end of the pulse is 1 centimeter away from where it was 1/100th of a second earlier. So we'll try more of this in class. If this feels strange, don't worry about it. This takes getting used to. There's no reason why you have to feel used to it and comfortable with all this stuff at this point. That comes with practice. So we'll do practicing over the next couple class meetings.